In this video we're going to compare addition polymers, which we learned about in the alkenes unit in the first year, with condensation polymers, which we've just been looking at. So addition polymers versus condensation, what are the main differences? So condensation polymers generally involve monomers that have more than one functional group. Those two functional groups react and a small molecule is lost. So the key feature is a small molecule such as water is lost from the reaction. Right, they normally contain ester or amide links, and that is very, very important. So remembering that our ester link is one where we have a C double bond O, and it's joined to two C chains. So two chains either side, and our amide link is our C double bond O, and we've got an NH, and we're joined on to some more chain. So ester or amide links. Addition polymers are made from alkenes. And so when you join them together, you don't lose anything. The double bond opens up and you form a continuous carbon chain. So if you remember from your alkenes notes, you've got a C double bond C, and you've got four things on here, and it really doesn't matter what the four things are. They can be anything. I'm just going to draw some coloured dots. So they can be absolutely anything. So they could be a CH3, they could be a whole of a benzene ring, they could be an alcohol group, they could be anything. So we've got four things. We are going to open up our polymer chain. So if we have a lot of these, the double bond opens up, swings around, joins on, and the four groups move themselves in position up and out of the way, and so they stay on their carbons. So there was a C there, and it wouldn't matter whether you started with the E or the Z, because once you form the polymer, because you've got single bonds, you've got free rotation, and free rotation means there is no E or Z in the polymer. So addition, there's nothing lost, we're just adding one to the other. It's an addition polymer. So what differences will you see? So condensation polymers are generally stronger. They're generally a bit more rigid. And that's generally because of the different intermolecular forces that you might find. So condensation polymers contain polar bonds. We've got that C to an O in our polyester, and in our polyamide we've got the C double bond O to the NH. Now I'm just going to add a little page and just have a look at something. You might say to me, well, in an addition polymer, which has got lots of C's like this, and there's groups sticking off, then there'll be polar bonds. So there could be a Cl here, and this one would be a H and wouldn't be polar, but there could be an OH here, and you might say to me, well, that's a polar bond, and that's a polar bond. And there is a polar bond there, but that would not allow the polymer to be disrupted, because to break this polymer, what you need to be able to break is the polymer backbone, the part of the polymer that runs all the way through the middle. I need to be able to chop this up in order to disrupt the properties of the polymer, to make it smaller, to make it less strong. Now when you take your condensation polymers, because in the middle of them every so often you're going to see these groups that have the polar bonds in the chain. Now because the polyester bond is in the middle of the chain, all of a sudden you've made a bond here that's susceptible to attack in the backbone, and as a result of that, that changes the properties of the polymer. So it's not that addition polymers don't have polar bonds, it's that they don't have polar bonds in the backbone, and the backbone of an addition polymer is a non-polar, very, very long carbon chain. The only thing you could do to an addition polymer is crack it like a very long chain alkane. So break it down by heating it up, and that is what recycling does. It cracks it down back into alkenes. You could think about which type of cracking would lead to a high proportion of alkenes that I could reform some new polymers from. Okay, so back to what we were looking at. So condensation polymers have got polar bonds, and that changes their properties. In polyesters, which were the ones on the left here, we can form permanent dipole-dipole forces. I'm not going to be able to fit that in. permanent dipole-dipole forces formed between the chains, whereas in polyamides, because we've got the N bonded to a H, then hydrogen bonds can, I should say, form there between the chains. Okay, so different types of intermolecular force. Just skip past that. Right, what we're going to do now is try to identify whether something is an addition polymer or a condensation polymer. So is it made from an alkene and has a carbon backbone, it's just carbons in a row, or is it made from amines or alcohols with carboxylic acids or acyl chlorides? Is it condensation? So what I would be looking for are some key features. In this case, I've got these OHs and these H's that I know I'm going to lose to form my polymer. So I know that this is going to be a condensation polymer. And then I would think about how that would join together to make the repeating unit. So remembering that I'm going to lose one of the H's off the amine, so I'll get to an NH. Then I've got CH2 2 times. Then I would have another N with a H, and a C with a double bond O, and a CH2 10 times, it tells me, and then a C with a double bond O, and a stick. And that would be our condensation polymer. And it would be an example of a polyamide because this is an amide bond. Now we look at the next one, and immediately I can see there's a double bond there, so what I do is I try to draw it out with this kind of structure. And as soon as there's a double bond that I think is going to be used for the polymerization, I know it's going to be an addition, and I would draw out the repeating unit. You don't need brackets for repeating unit. What you do need to be careful of is connectivity. Very important that this bond here joins the C to the C and not to the N or somewhere near the N. If you were going to draw that CN out, yeah, you would actually have a C and there would be a triple bond to the N like that. That would be how you would draw it out. So I want you to pause the video, I want you to fill in this table, see as much as you can do, and then when you unpause the video I'll fill it in and you can have a look whether you've got it right. Okay, so if we have a look through, the first one that you had to have a look at was actually made from a single monomer, and the way that I could tell that is I looked at the C double bond O and I noticed that there were no O's or N's directly attached, so there were no amide ester bonds in the middle of the molecule, so just the trailing bonds are the, in this case, amide bonds. You can be fooled by that little sticking off group. That's actually just a substituent, a chain. It's not part of the polymer chain. One of the things I always look for to decide whether something is condensation or addition is I follow my way down the trailing bonds and down the backbone, and I see if there's anything exciting going on, or is it just C's. Now, as soon as I've got this N and this C double bond O, I know that there's functional groups in the backbone, and with there being functional groups in the backbone, I know it must be condensation. And then I've pulled together my monomer by looking at putting a H back on the NH and an OH back on the double bond O. Now the next one, followed down from my trailing bond through to my other trailing bond, it's just made of carbons, and if it's just made of carbons, it's an addition polymer. And then all I've done is I've put the double bond back in the middle and then rearrange my groups so that it looks like my alkene. So again, I've gone through the trailing bonds, sort of down the whole backbone, which will include that whole benzene ring, and there's interesting things going on. So there's oxygens, and what I've done is I've broken all those ester bonds. They are ester bonds because it's double bond O to O, and I've put it into little groups and drawn out my monomers. There's two monomers there, a dicarboxylic acid and a diol. Okay, so again, I look at this, down the trailing bonds, it's just C's, and therefore it's an addition polymer. And down the trailing bonds and all the way down, is there anything interesting going on? Well, there's some oxygen, so it's not addition, it must be condensation. And there's no functional groups in the middle, so their functional groups must be at the end. There are plenty more of these to have a go at in your study pack, so if you want to practice, have another look in the study pack, see what you can do, and if not, get in touch with your teacher to help you out with this.